So I'd like to describe some of the fundamental parameters associated with heat transfer and their respective meanings. I'll make a table of the particular quantity we're interested in, its their respective meanings, the symbols that we typically use in heat transfer, and then the respective units. The first quantity that is important is thermal energy. And what I mean by that is it's the energy associated with the microscopic behavior of matter. And I mean more specifically the vibrations and rotations and different types of energy associated with the molecules themselves. And I'm not talking about bulk movement of molecules. They're stationary, and we just quantify this conceptually as their internal energy. The internal energy of matter is directly related to the temperature, and the symbol that we typically use for internal energy is the capital letter U. And we can draw a relationship between U and the temperature by using this equation, which says that the internal energy is proportional to what we call the heat capacity at constant volume, multiplied by the temperature, which could be above or below some reference temperature. All molecules have internal energy associated with them if the temperature is above absolute zero. So we say the internal energy is defined arbitrarily, that if the temperature is equal to the reference temperature, there's still molecular vibrations associated with it. There's still some absolute energy associated with it, but we arbitrarily call that zero when T equals Tref. The units associated with this are, we can say either joules, an extensive variable, or we can say something like joules per kilogram. So the total amount of energy by some amount of matter, or we can say the total internal energy per unit mass of matter. So the second quantity is temperature, and as I said, the temperature or the internal energy is directly proportional to the temperature of some amount of matter. So we say that the temperature is a means of indirectly assessing the amount of thermal energy stored in matter. So when you hear things like the large temperature, what we're really saying is that the matter has a large amount of internal energy. And we say when the absolute temperature in Kelvin or in degrees Rankine, if that equals zero, then we effectively are saying that that amount of matter has no internal energy. Symbol that we always see is that the temperature is symbolized by a capital letter T, and the units associated with it in absolute units is degrees Kelvin or degrees Rankine. In more common units, we say the temperature is in degrees centigrade or degrees Fahrenheit. What's meant by the term heat transfer is the thermal energy transport due to temperature gradients. So you know that heat flows from a high temperature to a cold temperature. So hot things tend to cool off and cold things tend to warm up. So we'll eventually figure out that the total amount of heat transfer is symbolized by the capital letter Q, and the units of this, we're talking about a total amount of energy. So the energy transported over some period of time, for example, the units of this are in joules. When we talk about the heat rate, what we mean is the thermal energy transfer per unit time. So we mean the rate at which heat is being transferred. And the symbol that's typically used is a lowercase q, and the units are in joules per second or watts. The difference between heat rate and heat transfer, what we're really saying is we're not concerned with the total amount of time or the total amount of energy that was transferred. For example, there would be 1,000 joules transferred over a minute. What we're really saying is over that minute, there is a rate associated with heat transfer. So we say something like joules per second. So it's independent of the length of time that heat transfer is occurring. What we're effectively doing to get between heat transfer and heat rate, we're taking the total amount of heat transfer and dividing by delta T, and that'll give us the average rate at which heat was transferred over this time interval. Let's take this one step further and define what's known as the heat flux. Heat flux is defined as the thermal energy transfer per unit time and per unit surface area. So what I've drawn is a small surface area and a large surface area. And if all things remain the same, we would consider that the rate of heat transfer in watts would be greater for the larger surface area than the smaller surface area, simply because there's a larger amount of area for heat transfer to occur. But what we're really interested in is accounting for this difference in surface area. So we take it and we want to normalize by it. We want to figure out, is there a parameter that would hold true for both of them? Is there a parameter that's essentially intensive and independent of the surface area? So let's do this. We're going to take the heat rate, Q, and divide it by the surface area. If we doubled the surface area, the rate of heat transfer, or Q, would also double. So this Q over A is a way to normalize for the surface area, and the notation that we use is Q double prime, where the double prime represents the flux. The units of this are in watts, the total rate of heat transfer, divided by meters squared, for example. Or we could say watts per foot squared.